The purpose of this lab was to analyze the movement of a swinging spring in simple harmonic motion in both the x and y directions. The main results of the video were to observe the principles of harmonic motion and to see that the energy principle was satisfied by the Earth spring and mass system. The object we observed in this lab was a spring of length 0.7 meters with a mass of 0.402 kilograms attached to the end. The spring is initially at rest, but it is pulled back so that it starts moving with a swinging motion similar to that of a pendulum, while also bouncing up and down due to spring forces. In analyzing the video, the point that the spring is attached to a pivot is defined as the origin, so the spring's initial position is about negative 0.7 meters in the y direction. The combination of the swinging motion in the x direction and the spring motion in the y direction caused the path of the motion of the spring to follow a roughly elliptical trajectory. By looking at the position data, we find that the period based on the x component of the motion is about 1.6 seconds, while the period calculated from the y component of the motion is about 1.4 seconds. While the periods are somewhat similar, they are not identical because the different components of the motion of the spring represent different types of simple harmonic motion. The x component of the motion is roughly accounted for by the oscillation of a pendulum, where the period is calculated by t equals 2 pi square root of L divided by g, while the y component of the motion is accounted for mostly by the oscillation of the spring, where the period is calculated by t equals 2 pi square root of mass divided by k. Using the initial values in the system and VPython, we created a computer model to approximate the y component of the motion of the spring. Delta t is set to 1 over 10.5 seconds to account for the frame rate of 10.5 frames per second in the original video. Calculations based on the model are also made for the kinetic and potential energy of the spring at every point. In this model, the orange bar represents the computerized model of the motion of the spring, while the blue bar represents the motion of the original data. While running the simulation, the graph of the motion of the model is plotted against the original data. In this graph, the green line represents the original data, while the red line represents the computer model data. As we can see from the final graph, our computer model very closely resembles the motion of the original observation. However, the original data does tend to deviate from the computer model more and more gradually as time progresses. This deviation can be accounted for by the work done by air resistance on the system. Damping caused by air resistance causes the amplitude of the simple harmonic motion of the system to gradually decrease. Outside of air resistance, no work is done on the system of the spring and the mass. Although energy of the mass is constantly converted between potential and kinetic energy as the mass oscillates between peaks and troughs, and work is done on the mass by both the spring and the Earth, between the Earth, mass, and spring, energy is conserved. We can see that the conservation of energy by applying the different energies of the mass. We run the simulation again, this time generating a graph where red represents the kinetic energy, green represents the spring potential energy, blue represents the gravitational potential energy, yellow represents the total potential energy, and orange represents the total energy. From this new graph, we see that the orange line representing total energy is constant, showing that the total energy of the mass on the spring remains the same despite changes in potential and kinetic energy. This is consistent with our knowledge of the energy principle, which says that in general, energy is conserved and that work done on the system is represented by changes in kinetic energy, as work is done on the spring by the Earth and on by mass by the Earth and the spring, the kinetic energy of the mass changes. Finally, we'll consider the situation for a computational model if we had set the origin of the system to the initial position of the spring, 0.7 meters in the negative direction below the pivot, instead of the origin we currently set at the pivot. The biggest change resulting from this different origin is that the gravitational potential energy becomes positive instead of negative, since the initial position is set to the origin. Spring potential energy remains the same because distance for the rest length is independent of the origin, and kinetic energy remains the same as well because it's independent of displacement. Despite the difference in the values of potential energy, total energy is still a constant line, showing that energy is conserved.